And Andrey, if you want to, perfect, and off you go.
Okay. So good afternoon to everyone, and thank you to the organizers for including me inside the program. So today I will present this working paper. It has the title "An Unconditional Quantile Vector Error Correction Model to Analyze Climate Heterogeneity." Scientific evidence from climate simulations and observations clearly indicates the existence of a global warming process mainly attributed to anthropogenic emissions of greenhouse gases. It has been also established that the climate change dynamics are not uniform across space and time. For instance, recent temperature trends in the Arctic are about twice the global average in a phenomenon which is known as the polar amplification. Even when we keep this geographical dimension constant, it has been also observed evidence of seasonally varying temperatures in the sense that winter temperatures are increasing at a faster rate than summer temperatures. Besides its ecological and environmental consequences, the existence of climate heterogeneity carries important implications for policy decisions. In a recent paper, Brock and Cepa-Padeas, they demonstrate that by ignoring polar amplifications may induce regulators to overestimate or underestimate the taxes on greenhouse gases, with the direction of the bias depending on the marginal damages and regional damages induced by these increasing temperatures. I believe that in this scenario, there is room for the econometric of in this scenario, there is room for the econometric modeling of climate systems to contribute by developing methodologies to effectively account for various forms of heterogeneity. A characteristic that this type of methodologies will fulfill is that they need to focus in characteristics beyond the mean. And in this sense, recently there has been some contributions that are uses, for instance, unit by unit or panel analysis, functional analysis, or that are trying to model like the whole distribution of the temperature and this relationship with the climatic variables. So in this paper, I propose a quantitative methodology to characterize the heterogeneity in the temperature in the temperature distribution dynamics and its association with several climate forces, for instance, the greenhouse gases such as the CO2. My methodology consists of a vector autoregressive model for the conditional characteristics of the temperature and the radiative forcing from greenhouse gases. So in here, when I talk about unconditional distribution and characteristics, I mean the mean and also the quantiles. Right? So I established an equivalence, between a one-dimensional energy balance model, which, as we are going to see later in the slide, it's a physical model used to predict temperature changes due to several climate forces, and establish an equivalence with my VAR model in its vector error correction form. I estimate the model using standard time series methods and accounting for the nature of the trends in the data. And my model can be used for several purposes, including first, the estimation of physical parameters, such as the climate sensitivity, which is a measure of the long-run response of the temperature with respect to changes in the radiative forcing from several sources. Second, unconditional forecasting given the underlying dynamics of the series. Third, identification of structural shocks and impulse response analysis. And fourth, conditional projections of temperature and the different hypothetical emissions or concentration scenarios. In this talk, I will focus in the first and in the fourth procedures, but you can imagine how the other may work. In my empirical analysis, I use data for the period 1880 to 2021, and in particular station level temperature data from the Climatic Research Unit and the radiative forces from I applied the methodology to different geographical scales, global, northern hemisphere, and Europe. Here I will focus my results in the empirical analysis to the results to the northern hemisphere, but we can give a look also if we want to the other scales. But it's important to note that this methodology is flexible enough to be applied to other situations in which we have enough data to compute the temperature distribution. And in this case, I'm thinking about, for instance, the application to Central England, in which we have daily observations during a long time of period, and we can use this higher frequency to estimate the distribution. This type of research complements the research based in climate modeling and simulation. And particularly, well, this is a data-oriented procedure that provides independent evidence of the global warming phenomenon. And in particular, is independent, for instance, of theoretical model specification or calibrations. And importantly, since this is a statistical approach, it provides the quantification for uncertainty through standard errors and confidence intervals and so on. This paper is related to two strands of literature. The first one is about the attribution and forecasting of global warming using historical data. Most of the studies are oriented in analyzing and modeling the mean. However, there are some recent contributions that incorporate heterogeneity, and there is where I have something to say with this approach I'm proposing. The second type of literature is the estimation and testing of time series models with deterministic co-trending. And here, for instance, I built on the contribution by Gu and Shintani in 2013 that they propose a test for the co-trending rank when the co-trending is among deterministic trends. So it's kind of an alternative. It's a different way, very related to co-integration, but for trending variables. More recently, in the Journal of Econometrics, Chen, Baid, and co-authors, they propose a simple method to estimate co-trending vectors whenever trends are can be in situation when you have a stochastic or deterministic trends. And I explore, I will in these two contributions, and I go a little bit beyond by exploring the correct error correction mechanism. So whenever we're analyzing relationships between temperature and radiative forcing, it is necessary to go back to the physics that are behind it. So and the physics here are provided by the energy balance models, which are climate models used to describe the change in temperature as a function of incoming and outgoing radiation. So in the most elementary model, the zero-dimensional EBM, a simple energy balance equation for the average temperature can be written as in equation number one, when in the left-hand side of the equation, we have the change in the average temperature with respect to time. And in the right-hand side, we have two terms. The first one in red is the radiative forcing, which is a measure of the amount of energy entering into the planet, while the second term is the outgoing radiation, which is assumed to depend linearly on the average temperature. Right? So one limitation of this approach is that it predicts the temperature of a theoretically spatially homogeneous planet and cannot account for spatial heterogeneity. So in this case, the model can become a little bit more complex. For instance, one-dimensional EBMs, they extend the model by introducing spatial dependence. So temperature is modeled as a function of latitude and heat is transported between adjacent latitudes in the direction from the equator to the poles. So at a given latitude theta, a simple one-dimensional EBM can be expressed as in equation number 2, where, well, in the left-hand side of the equation, still we have the change in the temperature, but now we are indexing the temperature by theta, the latitude. So this is kind of a local temperature. And this change depends in two terms. So in the right-hand side, the first term in red is the very similar to the term in the equation number one. It refers to the latitudinal net heat flux incoming versus outgoing radiation. But the second term in blue, it represents the energy gain due to latitudinal heat transport, which is assumed to depend linearly on the difference between the average temperature and the local temperature at a given latitude. A further generalization assumes that deviation at a given latitude predict the change in other latitudes, and then we face equation number 3, where simply we are allowing for a more, let's say, complete characterization of interaction in temperatures across latitudes. So I follow up similar reasoning to Pretis 2020, who he did this analysis for a zero-dimensional EBM. And here I propose an equivalence, and I show an equivalence between the one-dimensional EBM in equation number 3 and a VAR model in its error correction form. So the main assumption here is that at global over hemispheric scales, temperature and conditional distributional characteristics represent temperatures at different latitudes. And this is something that, according to the data, it looks like reasonable. And then we can discuss if that's the case. So if that's the case, for a given local temperature T of theta, it is possible to find an equivalent temperature quantile Q, and then we can write our equation 3 in this quantile version, simply replacing the temperature at a given latitude by the corresponding quantile, and then we face equation 4. So assuming stochastic processes and relying on a first-order Euler-Maruyama discrete time approximation, we can express the system in discrete time as in equation 5, where, as we see, each equation has the form of a vector error correction model, where the changes in the quantile adjust to the long-run relationships between the variables in my system. So particularly, in red, we have the long-run relationships between the radiative forcing and the temperature quantile. And in blue and green, we have the difference between the temperature, the average temperature, and the quantiles, right? So here, what is the characteristic of this model? Well, F, Q, and T are trending variables. And in practice, it is very difficult to establish what type of trends are present, either deterministic or stochastic. So, and here, then I rely in the proposal by Chen in order to be able to estimate these co-trending vectors, allowing for any type of trends, or for to use a robust method to estimate these co-trending vectors. And also, importantly, here, the difference between T and Q is in general trending. It's still trending. So why is that? Because this climate heterogeneity implies that not all the quantiles of the distribution are going to evolve at the same rate. And so if I take the difference between the two of them, so it's still some trend is going to be present. So what I do here is, so I allow the co-trending vector between T and Q to be different from y minus 1 and just to be generally estimated using the Chen method. So my methodology can be summarized in this slide. So in the first step, I estimate the unconditional distributional characteristics of temperature using historical data. Second step, as I test for the co-trending rank in the sense of Wunsch-Mintani, the number of linear combinations of variables that are non-trending. I estimate and test the co-trending relationships implied by my model using the approach of Chen, Bait, and co-authors. And in step 4, I estimate the short-run dynamics of my model in an equation by equation procedure, where again, as I said, the co-trending vector between Q and Q is allowed to be different from 1 minus 1, and in general is allowed to be 1 minus beta. It's important to note that this methodology is flexible to be applied in situations, not just when we have this geographical variation, but also can be applied if we have, for instance, higher frequency data that allow us to estimate the unconditional distributional quantiles, but then the interpretation needs to be adapted to that situation. So in my empirical analysis, so station level data from the climate research unit, radiative forcing from different sources, for instance, CO2, anthropogenic, natural, or the total radiative forcing. The total is the one that I'm going to show in the baseline, are obtained from the data set by Hansen, which is the typical data set that is used in the empirical analysis. And I find evidence of deterministic trends in the temperature distribution and evidence of the radiative forcing as being like integrated of order 1 process. But remember that the procedure I'm going to use to compute the co-trending vectors and so on are robust to the type of trends. So I start with a very simple parsimonious model in which I include 3 quantiles, 5%, 50%, and 95% in order to represent the different parts of the temperature distribution. I include also the average temperature, and I include the total radiative forcing. And then I find meaningful and significant relationships between the unconditional quantiles and the average temperature. And it can see here in this table, so where I report the co-trending vector between each quantile and the average temperature. And then as we can see, the co-trending vector decreases with the quantile level. So implying that the co-trending relationship is stronger at lower quantiles. And this is something which is consistent with the phenomenon of polar amplification, like the lower quantiles are increasing at a faster rate with respect to the temperature, to the average temperature. So I also find evidence of heterogeneous and significant co-trending slopes between the unconditional distributional characteristics of temperature and the radiative forcing. So in here, so we see again that the co-trending slope decreases whenever the quantile level increases. And this is important because this co-trending slope is a measure of the long-run relationship between the two variables and is used to compute what is called the climate sensitivity. So I use these coefficients to estimate the climate sensitivity. So how do I interpret this graph? So basically, I say if the radiative forcing is double, then the quantile 5% is going to increase around 3.6 degrees, while the quantile 95% is going to increase around 1.6 degrees, right? So what I'm showing here is that the responses of the temperature to the external forcings are quite heterogeneous, and as expected by the dynamics of the series, are stronger in the lower part of the temperature distribution. So it implies, and it has some implications in terms of economic and societal and also environmental implications. I estimate the model here. I'm just presenting like the adjusting coefficients, and then looking at the significance of the coefficients, it looks like it's consistent with the predictions of the one-dimensional energy balance model in terms of what we observe here. And then we can use the estimated model to produce, well, forecast, like to long, medium, and long run forecast, to produce to identify shocks and conduct input response analysis and so on. But I want to focus in the conditional forecast given hypothetical future emissions scenarios. So in here, I will consider the shared socioeconomic pathways scenarios that describe potential future paths of socioeconomic development with implications for energy use, land utilization, and greenhouse gas emissions. So the SSP framework outlines 5 broad narratives. So in here, so it doesn't mean that this is going to happen, but you hypothesize about different situations that we can face in the future. So for instance, SSP1 assumes that in the next decades, we are going to become more aware of the environmental problem. So we are going to adopt mitigation and adaptation strategies that will take us to the green road, right? And it has some implications in terms of the future expected emissions under these conditions. In the other hand, for instance, SSP3 is assuming that so nationalism is gonna increase. So it's going to be difficult to coordinate countries to take decisions regarding climate change. And then it implies, for instance, high challenges to mitigation and adaptation with implied path of future emissions. So the APCC report used this framework to construct certain scenarios implying different trajectories of emissions and warming. And here, just 5 representative of them. These are the ones that use the. So we see here the implied total radiative forcing under different scenarios. So I use this external data and I produce like conditional forecasts given that I have this information. Okay. So this is how like the distribution projections looks like. So here maybe it's not very informative. What is informative here is the change. So it's this table that shows how the temperature would change under each scenario. So and what I can observe here is that for any scenario you can focus. So I'm comparing here the change in the prediction in 2100 versus the average between 61 and 90. And we see that the responses are going to be quite heterogeneous. Okay? So, okay. So just to conclude, so I do some complementary analysis. So for instance, I can introduce more quantiles in order to enhance the model and to provide a wider characterization. This is what I observe. So in general, the heterogeneity maintains whenever I include, this is the climate sensitivity. So I can use, so I can apply the methodology in other situations whenever I can estimate this distributional characteristics. So here I have the application to Central England that I don't have much time to talk about, but here are the estimated climate sensitivities that looks like a less marked pattern of heterogeneity is obtained. And well, there are some limitations, of course, with this type of methodology. So for instance, 150 years of data are too short to disentangle long-run climatic relationships. Fair enough. So unconditional quantiles can imperfectly represent temperature at different locations. This is something that also can be true. All the radiative forcing that we are assuming is homogeneous across geographical units, while there are some local factors that can influence. So from these limitations, I think that there are interesting paths for future research that are like doable. So I think I will stop here. So thank you very much, and I will be very happy to discuss and to hear your suggestions. Thank you.